All right. Hello, everybody. StreamYard is telling me we are live. So as I always do, I am going to wait to see it myself on YouTube, which I do. I'm just going to make sure I can hear myself, which I can. Great. So now we can get into it now that it seems like the tech is working. If anybody catches any problems with the audio or anything, just let me know in the chat on YouTube. So I am really excited to introduce my guest today. With us today is Dr. Michael Behe. He is a professor of biochemistry at Lehigh University, a senior fellow at the Discovery Institute, the author of Darwin's Black Box, The Edge of Evolution, Darwin Devolves, and most recently, A Mousetrap for Darwin. And if I missed any in there, please feel free to add to that. And we are here today to talk about irreducible complexity because it is the 25th anniversary of the original publication of Darwin's Black Box. So, Dr. Behe, if there's anything you want to add to that, please be my guest, and then we'll get started.
No, that's great. Let's get into it here.
Okay, cool. So the thing I want to start with, I want to go through in as much detail as possible. Very specifically, the irreducible complexity hypothesis. What we do on this channel for you and for the viewers that aren't familiar with it is that we take the scientific claims of creation science, broadly defined, and we strip away any context, any philosophical overtones. We say, let's examine this as a scientific hypothesis and see how it works and how it holds up. And so we talk about things like Dr. Nathaniel Jeanson's time to most recent common ancestor calculations, or Dr. John Sanford's genetic entropy, and of course your concept of irreducible complexity. So what the place I want to start is actually not specifically the definition or framing the hypothesis. I want to start with probably the most common criticism we hear of this idea, which is that it is unfalsifiable, that you could say, oh, well, here's how this system evolved, here's how that system evolved. And the ID proponent could always say, well, what about this other thing? What about this other thing? And you could just kind of just keep on going and finding some other system, the evolution of which we have not specifically documented, and say, well, that's the thing that can't evolve. So let's get that out of the way first. How do we falsify this idea like any other scientific hypothesis?
Well, first off, to falsify it, yes, you could show, Darwinists could show that something that he or she thought was irreducibly complex had indeed evolved by random mutation and natural selection. Say a two-protein system that both proteins were necessary. And if that were the case, I don't know about other people, but I would admit then that anything of that degree or lesser complexity could evolve by a Darwinian process. Things of greater complexity, maybe not. That has yet to be shown. But things of that degree or less, that'd be fine. So if somebody showed that, say, a bacterial flagellum could evolve, I think I would be silly to say that, oh, well, the blood clotting system couldn't evolve by Darwinian processes. So I think that's not really a valid criticism.
Okay, so if you can show that and I really do want to dive into the nuts and bolts of this, like how to quantify those different degrees of complexity in a little bit, but just to make sure I have this right. So if we can document the evolution of a system, then we could say, okay, that system, we showed it, say in the lab, we have a cell that never in its evolutionary history had whatever characteristic, and then it evolves it. And we say, okay, we've now observed that this thing can evolve. And anything at that level of complexity or less, it's reasonable to say that stuff can evolve. Evolutionary mechanisms are sufficient. Is that fair?
That's correct. With a few caveats. One is that yes, you can document it in sufficient detail. You can't just show, well, these genes are similar to these genes, and we imagine that this could have happened. And let's see, it's the perils of getting old. I've forgotten what the second point was, but
that's okay. When it comes back to you, just interrupt me and we'll add it. Okay. So we have a criteria for falsification of the hypothesis, broadly speaking, of if irreducibly complex, yada yada yada. We'll fill in the blanks in a few minutes over the next few minutes. Therefore, problem for evolution. But we could say if you can directly document something, then that's going to invalidate that hypothesis for anything up to that level of complexity.
That's right.
Okay.
And let me, I remembered the other thing.
Perfect.
And it's got to be shown to be able to be done by Darwinian processes, because a lot of investigators actually kind of guide their systems in the directions they want it to go.
So that is an extremely important caveat, and I am going to come back to that in a little bit as we kind of very specifically kind of tease apart the nature of this hypothesis. Okay, so those are our falsification conditions. So the obvious question, and possibly the logical place to start, would be, let's define irreducible complexity. How do we say this system is irreducibly complex? And I'm going to show on screen and quote from the 10-year anniversary edition of Darwin's Black Box, because I want to make sure I'm getting it exactly right. I'm not leaving anything out here. So this is the definition from the 2006 version. An irreducibly complex system cannot be produced directly, that is, by continuously improving the initial function, which continues to work by the same mechanism by slight successive modifications of a precursor system, because any precursor to an irreducibly complex system that is missing a part is by definition non-functional. An irreducibly complex biological system, if there is such a thing, would be a powerful challenge to Darwinian evolution. Since natural selection can only choose systems that are already working, then a biological system cannot be produced gradually. Then if a biological system could not be produced gradually, it would have to arise as an integrated unit in one fell swoop for natural selection to have anything to act on. And then there's a follow-up paragraph there that I think is possibly more important. Even if a system is irreducibly complex and thus cannot have been produced directly, however, one cannot definitively rule out the possibility of an indirect circuitous route. As the complexity of an interacting system increases, though, the likelihood of such an indirect route drops precipitously. And as the number of unexplained, irreducibly complex biological systems increases, our confidence that Darwin's criterion of failure, which I think is a reference to his eye description that could not be produced.
Numerous successive slight modifications.
That was the one, yeah, exactly. Has been met, skyrockets towards the maximum that science allows. So that was from 2006. It's now 2021. I want to make sure that this still applies as the working definition of the criteria for saying, okay, this is a system that is irreducibly complex.
Sure. Mm-hmm. Yes, it does.
Okay, cool. Great. So that's a great work, nice, clear definition. So the next thing that I really, and this is where I think we'll really kind of get into the nuts and bolts here, is the hypothesis that flows from this, because it's easy to come up with a definition. Irreducibly complex means X. Here's the definition. And we could go around and identify systems that meet those criteria. That's really straightforward. I think the contentious part of your work here is if irreducibly complex, then some problem for evolutionary theory, right? Therefore evolution has a problem writ large. So what I want to do is figure out specifically what that hypothesis is. If we identify a system as irreducibly complex, then what?
Well, if it is irreducibly complex, then as Darwin wrote in Origin of Species, then it could not be produced by numerous successive slight modifications. For your listeners, in a section of the Origin of Species called Organs of Extreme Perfection and Complication, Darwin wrote about the vertebrate eye, and he listed a number of parts, but then he thought he could see eyes that kind of lined up and might serve as examples of evolutionary intermediates, although they weren't. And he acknowledged that. And he said that, yeah, well, if we had this complex system, like an eye or something, that could not be produced by numerous successive slight modifications he said his theory would absolutely break down. And he added a caveat. He said, I haven't been able to find anything so far. But in this, he was emphasizing that his version of evolution had to be very gradual. It had to proceed in tiny steps over long periods of time. But he didn't say it, but by random processes, because he knew that if things appeared rapidly in large leaps, then it would look like something other than random processes were in. So he always insisted on gradualness, and irreducible complexity challenges that gradualness.
Great. So, as you know, Darwin wrote that in 1859 in Origin of Species. It's now 2021. So this hypothesis, is it strictly for Darwinian mechanisms, or does it apply more broadly to all the other mechanisms of evolution that we've figured out since 1859? So what I'm asking is, if you say, if a system is irreducibly complex, it can't evolve via Darwinian mechanisms, or it can't evolve, period. Right?
It cannot evolve by any unintelligent process. So any other process which people think might be non-Darwinian will not be able to produce it either, if it's not guided or directed or some such thing.
So that's inclusive of, so the hypothesis is inclusive of all evolutionary mechanisms, then, not just strictly Darwinian mechanisms. So we're including things like neutral evolution, horizontal processes, exaptation, anything we do, epigenetics, evolvabilities of phenome, all that fun stuff that we figured out since 1859 is included under the umbrella of, if we have an irreducibly complex system, it can evolve via any evolutionary processes, period. That's the hypothesis.
Okay. And let me just kind of explain my position. I think, along with many Darwinists who say this, I think that almost all of those other mechanisms are pretty much Darwinian anyway, or they could be easily accommodated. They might involve processes that Darwin didn't know about, but if you're thinking of random changes and then selection, I would say they are under that broad umbrella.
Okay, so you're defining Darwinism as all evolutionary processes.
No, but a lot of them. And if somebody wants to tell me that it is something independent of a Darwinian process, I'd like to see the details before we go forward.
I mean, just to make sure everybody's on the same page here, Darwinian evolution is very strictly mutation, variation, natural selection. From there, we get a whole bunch of new mechanisms, starting with the modern synthesis in the early 20th century. And then since then, starting with the 1950s and 60s, we've got a whole bunch of additional mechanisms on top of that. So we've got our neutral theory, which wasn't really formalized until starting in the 60s and really formalized in the 80s. You've got epigenetics, relatively new, horizontal processes, any large-scale mutations, gene or genome duplications, anything like that is non-Darwinian. Epigenetics is, of course, non-Darwinian. Plasticity, the idea of evolvability itself being a phenotype, exaptation, taking one thing and then switching the function. Those are all non-Darwinian mechanisms. And I want to make, the reason I'm harping on this is I want to make sure I have this crystal clear. When we say a system, it has irreducible complexity, does it preclude evolution by all these mechanisms, or just the ones from 1859, or just the ones from the 1940s?
I'm glad to say it precludes them by all those processes you just mentioned. I just want to say that, in my mind, I consider them all random changes. Remember, Darwin didn't know about mutations or anything. He said random changes plus natural selection. And you've got to look at each of them carefully. I think neutral mutation fits happily into Darwinian evolution, except that the mutation has a selection coefficient of 0 instead of a negative or a positive one. So that doesn't strike me as a big deal. And gene duplication, that's fine. That's one event, though. So yeah. So any unguided processes.
All right. Any unguided processes. Got it.
Right.
So what we're looking at here is then, and again, correct me if I'm wrong in my understanding, but it seems like we have kind of two sides of this hypothesis. We have the affirmative side and the negative side. Then you have irreducible complexity in a system. You identify a system as irreducibly complex. You say, well, that system, because it meets these criteria, couldn't have evolved. And then the other side of that, related but not directly flowing from it, is if it meets these criteria, then it was designed as the product of some intelligent force, right?
Yeah, those are completely, well, yeah, I go at length and explain how we detect design later in my books. Irreducible complexity is a good example of it, but there are other considerations one has to keep in mind. But yes.
Okay, so this is now we're kind of right where I want to really get into some nitty-gritty details of specific systems here, because the first problem I have with your hypothesis, and for anyone watching who doesn't know, I'm an evolutionary biologist. I very strongly object to intelligent design and irreducible complexity. The first problem I have here is that we just went through the criteria for irreducible complexity, and you said if you have this system, it can't evolve via unguided mechanisms, and yet we have directly documented, in some cases observed in a laboratory setting, the evolution of systems that meet these criteria. And I mean, we go through a list of them. I know you're familiar with the Lenski citrate plus line, where in the Lenski long-term evolution experiment, one of the 12 lineages evolved the ability to do aerobic citrate metabolism. That trait meets the criteria for irreducible complexity. Another example I know you're familiar with is HIV group 1, HIV1 group M VPU, and the new biochemical activity of tetherin antagonism meets the criteria. One of my favorites that was recently discovered was the extracellular transmission of plasmids via liposomes, which is an extremely complex process that was documented in a laboratory setting and has never been known anywhere else. But you could put together all the steps in that, and that's certainly an irreducibly complex system. And I could go on. There's lots of examples of this that we could document in nature or in the lab that meet the criteria.
I'd love to look at the papers for the other systems, but why don't we stick with Lenski's?
I would love to.
Lenski's criterion. Yeah, as you mentioned, in Lenski's long-term evolution experiment, around the 30,000th generation, one of the strains of bacteria acquired the ability to be able to grow on citrate. Okay, so citrate was a chemical that was in the growth medium for technical reasons, but normally E. coli cannot eat that, and it can eat it when there is no oxygen around. It turns out that it can't eat it, though, in the presence of oxygen. And in Lenski's experiment, oxygen was there all the time. And so this seemed to be a new ability, and he made a big deal out of it. But he didn't originally know what the mutation was that allowed that to occur. And later on, when it was tracked down, he showed that a fragment from a nearby gene, its promoter, which controls whether the gene is turned on or turned off, for anyone listening who hasn't heard the term, its promoter was accidentally duplicated and placed near a citrate transporter gene that was already there. It was already there to transport citrate into the cell in the absence of oxygen. But now with this switch, this on switch that could also turn it on in the presence of oxygen, it was expressed. And it turns out it was the only thing missing from the ability to metabolize citrate in the presence of oxygen. It just needed that element. So essentially, it rearranged a couple of things.
So Couple of corrections there. First, it wasn't the promoter that got duplicated. It was the CYP gene itself. The transporter got duplicated. So you have the original module with the anaerobic promoter, CYP, and then downstream of that, you had an aerobic promoter, and the CYP gene got duplicated down into the control of that second promoter. It wasn't the promoter that got moved. It was the gene itself that got moved. The second thing is that there were other things that were required for that trait to appear. There was upregulation of, I'm going to get the name of the gene wrong. I apologize, everyone. I think it was DCTA, which is a succinate or succinate transporter, because the CYP is actually an antiporter. So you get the citrate in, but then you lose the succinate and some other stuff. So you got to bring that back in. So you have to upregulate that other gene. And then there was some other mutations in something related to acetate metabolism, which, if I had to guess, had to do with feeding into the citric acid cycle with acetyl-CoA, but I couldn't tell you any more than that because biochemistry for me was a long time ago. But so the first thing is that it was a duplication of the gene, the transporter, not the promoter. And the second thing was that it was multiple mutations were actually required for this. And the important thing is that it was unselectable until you had all of them. And the CYP duplication on its own was actually strongly deleterious because it turns out to be a bad trade. If you just bring citrate in while you're getting rid of other stuff, that's a really bad trade, unless you can do the other work of bringing that other stuff back in and doing this other thing with acetate metabolism. So it does meet the criteria for irreducible complexity in that it has multiple independent requirements where you can't have selection for any of those intermediate steps. It can't form in a stepwise pattern where you're optimizing the function a little bit at a time. Okay,
let me address your concerns in order. First is that, okay, so the gene is duplicated and placed in front of a promoter that is works in the presence of oxygen. Okay, I misremembered that. But it's still the same thing. All of the information was there. It was kind of rearranged. And I've written about this before, and I consider that to be kind of a horizontal evolution. You're not making new, what I called functionally coded elements. You're only rearranging them. Okay, still, it's interesting, but I never say that nothing can evolve. The second thing is that the other things that you speak about, you talk about succinate transporters and acetate and so on. That's interesting, but they aren't parts of the system, okay? When I talk about irreducibly complex things, like, say, a flagellum, which needs these parts to work, I'm not talking about, say, some metabolic requirement that the pH has to be something and some unrelated part can affect the pH. It's got to be the system. I used an example in my book, Darwin's Black Box, which is accessible to the lay public, of a mouse trap. And the mouse trap is it has definable parts. If you say the mouse trap won't work if the temperature is too high, or if it's immersed in some liquid or something, well, okay, but I wouldn't count those as parts of the system. So it's interesting that other things are necessary for it to work at all. For example, it needs food, and it needs temperature, and it needs other things too. But I do not consider those parts of the system.
Okay, so a couple things there. First is that the rearrangement point is not relevant to the question of does it qualify as irreducible complexity. And I think it's arbitrary to say, well, the succinate transporter is not part of the same system as this citrate antiporter, when it's all part of the metabolism of the cell. And to use another example that you used as irreducibly complex, you could look at something like blood clotting, for example, where we have all these different factors and proteins and things, and you need certain vitamins, like vitamin K you need. Well, are we going to say if there was something with vitamin K was a problem? Would we say, well, that's not part of the blood clotting signaling cascade, so that's not part of the same system? Well, no, I think that's silly, honestly. I think we would say that vitamin K synthesis is an integral part of the blood clotting system, and it's one of the components you need, where if you have a vitamin K deficiency, then you have a problem with blood clotting. And in the same way here, if you have the CYP-T duplication, you could bring citrate in nice and efficiently.
Mm-hmm.
It's still metabolism. If you're getting rid of the succinate, you can't bring it in, then that's part of the same system. But so if you want to respond to that, you can. But we could focus on an example where it is specifically like the same protein, and we can look at it, more specifically that way.
All right, let's do that, because just in my mousetrap example, to make it more understandable for folks who might not be biochemists or scientists, it may be the case that you need something in the factory that produces the spring, or you need a fuel to fire the furnace to shape the holding bar. And if that was missing, then you couldn't even make a mousetrap. I myself don't count that as part of the system. You could go back to the Big Bang if you wanted to say what was necessary for something to work. Right? I think focusing on the immediate proximal system is the way to go.
Correct me if I'm wrong, because like I said, biochemistry for me was first year of grad school. I won't say for the audience how long ago that was. You're the biochemist. But isn't succinate part of the citric acid cycle?
Sure.
Okay,
Yeah.
so it seemed like that would be part of the system of citrate metabolism then.
Yeah, but we're not talking really about a citrate metabolism, because we're just talking about getting it into the cell. And all you really need after you've got it into the cell, we have all the other enzymes present to allow it to work. Whether or not that's beneficial or not, it can still work. Even without those other mutations, it could still work. It might not be helpful to the cell to grow, but it could still work.
So you're talking, okay, so I see the distinction. You're talking about the genetic system of citrate permitting aerobic citrate metabolism rather than the underlying metabolic system. That's the distinction that we're making here. Okay.
Right.
So let's look at an example where it's all one gene and it can't be part of a different system because it's all one gene. And that's the VPU protein in HIV. So in HIV1 group M, which is one of the major groups of HIV, there's a teeny little protein called VPU, and it does a thing, and we don't need to go into it doesn't matter what the thing is. It does a new thing in HIV compared to the ancestral SIV protein. And the reason it does this is because there's part of the human immune system that's different from the chimp immune system. The biochemistry of it doesn't really matter, except for the fact that in order for this new mechanism to work, the VPU protein in HIV1 group M has a new binding site to a human immune system protein called tetherin, and that binding site involves between 4 and 7 amino acids. They documented 3 directly. So these 3 amino acids are required for this binding to happen. And they're in this one region of VPU. And then there's this other region of VPU that's also required, and that has at least 1, possibly up to an additional 4 amino acid specific amino acid substitutions that are required for this activity. So we have now, and I should note that there have been lots of work on this where you need all those mutations to have this it's called tetherin antagonism is the novel activity. So we have between 4 and 7 specific mutations that are required in a single protein for a novel protein-protein interaction. You can't select the intermediate steps because it doesn't work if you only have the intermediate steps. You could do the point-wise substitutions and show that. That's an irreducibly complex system by the criteria that it can't evolve of successive slight modifications of increasing function on the ancestral system. All of those changes are within one system. And considering HIV hopped over into humans around 1930, that's been pretty, we've documented the evolution of that one. We got to witness it in the last century. So that would also seem to be a clear-cut example of a system that meets the criteria evolving.
Okay, so tell me what the activity of the system is.
So it does two things. It forms a pentamer. So normally these VPU proteins don't bind with each other, but what they do is they form a pentameric ring that is an ion channel, and then they also associate with this tetherin protein, and the combination of the ion channel plus associating with the tetherin molecule inactivates the tetherin.
So the ion channel is the result of a VPU forming a pentamer.
Yeah, so
probably inserting itself into the membrane of the cell and
correct.
Essentially allowing it to leak.
Yep. So it binds. So the irreducible part is the antagonistic activity where it requires multiple new binding sites. Where you could picture, a right hand and a left hand to hold on to the adjacent molecules, plus a backhand to hold on to the tetherin. So you have multiple new binding sites that are evolving, multiple amino acid changes that are required. You can't select for the intermediate states.
Well, okay. I don't. I would have to look at that in more detail. I think I've spoke about VPU maybe 15 years or so ago in some correspondence, but time flies. And I also said in my definition of protein binding sites in Edge of Evolution that the introduction of a virus into a non-viral host developing a binding site is not one that I would consider undoable, because as I wrote down, there's many targets of opportunity for binding sites to occur, and any one of them has a good chance of messing up the cell. Because cells need much of their machinery to function. Additionally, I also noted one always has to make distinctions here, and I noted that HIV is, of course, a retrovirus which occurs in enormous numbers, and it has very high mutation rates. So that a virus that has multiple mutations would be expected to occur in every infected organism pretty much every day, so that the occurrence of triple mutations in HIV is not much more impressive than single mutations in genes in mammals or other large organisms. And so, in my definition of irreducible complexity, could you go back a slide? I even forget this stuff.
Do you want the first half or the second half?
The first half.
Yeah, here you go.
Okay. Let's see. I'm going to continue my slides. Successfully. Okay, maybe it is the second half.
There you
go. Okay, I can't see it right here, but in the definition, I said that the parts are well matched to each other.
That wasn't in this part, but yes, there's the phrase well matched. Yeah.
Yeah, well matched. And that depends on what you got. If you have a zillion parts, then is one of them going to be able to match another? And the answer is sure.
So I think we need to amend the hypothesis then, because now it seems like it's not an all or nothing thing. It's context specific. It's dependent upon population size, mutation rate, genome size, mutation saturation, that kind of stuff. And if you have a population like HIV within an individual, mutates really fast, enormous population, you would expect to see not just mutation saturation, but you'd expect to see every possible combination of 2 or even 3 mutations in there. So is it the case that it's irreducibly complex, cannot evolve via any unintelligent process unless the population size is X and mutation rate is Y, and et cetera?
Well, I dealt with that in my later books too, in The Edge of Evolution and in Darwin Devolves. In The Edge of Evolution, I said, well, okay, yeah, it is the case that it's population size and mutation rate and stuff like that. So let's take a look at what evolution does, in fact, do when it has the chance, when it has enormous population sizes, when it has a very, very fast mutation rate. And I noted in that book that in the case of HIV anyway, that there have been more viruses and they have undergone more mutations likely than all the cells that have ever existed on Earth in the past 4+ billion years. And we can ask then, well, what has it come up with? It's come up with, a new binding site here. And that's pretty much it.
Well, so first of all, note that that's not the case. HIV has come up with a lot of new stuff, including several ways to do the thing I just described. Every major lineage of HIV actually does it differently. Group M does it with a number of specific ones. I forget if it's group N or O does it with a string of, I think, negative charges, but I forget which one. There's another way to do the same thing.
Yeah, by switching the amino acids to other negative charges. So instead of using aspartic, maybe you can use a serine that gets phosphorylated or a glutamic instead. Well, okay, big deal. I consider that to be evolutionary drift, that it's doing pretty much the same thing by slightly different means.
Okay, so I think we need to add a criteria for falsifiable here, and if Michael Behe thinks that it's significant enough, unless there's a quantifiable limit, right? So what is that quantifiable limit then? Because I've given you 2 examples that they meet your criteria, steps where you're not building intermediate functionality. It's all or nothing. You can't select the intermediate steps. And well, that doesn't really count because it's not the same system. And that one doesn't really count because it's in this virus where you're trying out so many mutations. Okay. So where's the limit between what irreducibly complex things can evolve and what things can't evolve?
Okay. Let me just say to start that I'm sorry that this tests your patience, but you have to make distinctions when you think about these things. And you can't just say, well, this, that, and the other thing, because as I've always written, it's clear that chance can do some things. Luckily, some sickle cell mutation arises. Hey, that's got a binding site for hemoglobin for itself. And it can help in, of course, malaria-ridden regions. So these are not quibbles on my part. These are valid distinctions.
So wonderful. So I'm asking you, where is that line? So if, for example, VPU can evolve this new function in not that many years, if we can have this CIT+ system evolve within a few thousand generations, if we can have plasmids evolve extracellular transmission via liposomes, if animals can start down the process of secondary endosymbiosis, all of these examples are things that we've directly observed, and they require a number of unselectable steps to get anything like the phenotypes that we observe either in the lab or in nature. And my question is, if some things that meet the criteria that we established a little while ago can absolutely evolve, and we've documented their evolution, although not through strictly Darwinian means, I will say, then where do we draw the line in terms of this hypothesis? Where do we say, okay, this system can evolve, this system cannot? Earlier, you said, well, anything that we've observed, right? We could say, okay, we've observed it, therefore, anything of that level of complexity, great. We could say that that level of complexity can be the product of evolutionary processes. Now, back in January, though, you did an interview with Dr. Sean McDowell, and you said kind of the inverse of that. You said, well, if we can't document something simple, like a disulfide bond, then we can't reasonably say that anything more complex than that can evolve. If we can't document the simple things, then what right do we have to say that the more complex things evolve? Mm-hmm. Which is contradictory with what you've said here, that once you've documented a thing, you could say, okay, that's now represents at the very least a ceiling, right? And everything below that, even if we haven't directly documented it, we can say it evolves. So square this circle for me. Where's the criteria based on irreducible complexity that's quantifiable, that allows us to say this thing, it meets the criteria, but that can evolve. But this other thing, the criteria can't.
When you know the characteristics of your system, when you know the number of organisms, you know the mutation rate and things like that, when the event would much exceed the probability of it occurring in the time that you are watching the system. I would say that. For example, I would not be surprised if HIV developed a disulfide bond in one of its proteins, but I would be real surprised if an elephant, if the line of elephants mutated so as to develop such a feature. So as I said with Sean McDowell, yeah, if you look in the biology literature, if you look in the evolutionary biology literature, many theorists are still perplexed by how disulfide bonds could evolve. And for folks who don't know what they are, they're essentially just a simple feature of a protein where one amino acid residue called a cysteine forms a bond with another one. That's called a disulfide bond. And the problem with that is that you need two cysteines to make one disulfide bond. You can't do it with one. And so this isn't just me. If you look in the literature, for folks who are wondering about this, it's still a big open question, even though it's the simplest cooperative feature, I think, in biochemistry.
To be honest, this sounds an awful lot like the thing I started with, the criteria for falsification, and that this ends up being an endless series of mobile goalposts. It's sounding like that may be a valid critique, because we're jumping around to these different systems. But what I've asked for a couple of times is if we have a quantifiable criteria where we can look at a system and we can say, this system it meets these criteria, therefore it is certainly the product of design. Now, I've given you a couple examples where systems meet the criteria for irreducible complexity, but we've witnessed their evolution. So I think it's clear that the original way that we defined irreducible complexity here isn't a both sensitive and specific filter, right? No false positives, no false negatives for things that cannot evolve, because we've documented things that can evolve that meet those criteria. So what I would love to know is how do we document exactly where that, like, quantifiably, this system with this many components in this population. You gave an example with elephants, right? But elephants don't exist in a vacuum. Elephants share common ancestry with other vertebrates and other bilaterians, et cetera, et cetera, et cetera, right? I don't want to put a position in your mouth, but I believe I've heard you say you accept universal common ancestry. I don't want to characterize your positions incorrectly.
Sure.
But
That is correct.
so it's not just that we're looking at elephants in a vacuum on their own. We're looking at the entire 3 billion year evolutionary history, or however many billion year evolutionary history of eukaryotes, for example, right? And so given that evolutionary history and all the tries, if you will, for different interactions to occur, how do we look at a specific thing and go, there's no way that evolved over all that time. There's no way that thing specifically could have evolved. And what it sounds like you said earlier is, in the time frame we're observing it, if your probability is lower than the number of tries, essentially. Well, that sounds like an argument that is not falsifiable, because it just means once you expand your window of what you're looking at, then your criteria have changed. So please, I want to give you an opportunity to explain this, because I really do want to know what the criteria are that allow us to say this thing could not have evolved.
Well, okay. This is both an empirical argument. It's an empirical argument, so it depends upon observations. Okay. If we said we live in a multiverse and that each universe has zillions of people, and now what are the odds of getting a new protein binding site? Well, they're real good if you're living in a multiverse. So it depends on what we got. It depends on what science has discovered about the cellular basis of life and DNA and the mutation rate and all sorts of that stuff like that. And it depends on what we discovered about how life works, about the molecular machines and interactions, genetic codes, and so on. What does it take to build those things? So again, you can define, you can look for irreducible complexity in, and let me just emphasize before I go into that you are looking for the very minimum. Okay, you're saying, well, yeah, but in HIV with this, we can get this little new binding site here, and why that fits your definition. Why don't we, it's kind of like seeing faces in the clouds or something. You're saying, that we can't recognize faces because here's some instances where faces seem to appear in the clouds. But if we go to, other systems, which have astonished scientists throughout the decades, such as, say, the flagellum, which I'm sure you're familiar with, and the blood clotting cascade again, and even simpler things. I think, those, are indisputably beyond what we're quibbling about here. Additionally, in my other book, I've shown why those irreducibly complex systems can't be approached, because in the book Edge of Evolution, I showed how difficult it is even to get 2 coordinated mutations in a cellular system. And in Darwin Evolves, I just want to say
that was Plasmodium, right? Was that the Plasmodium example?
What did I say?
No, you said in a cellular system, and I just want to be specific. That was the Plasmodium example with the resistance
parasite. Yeah. Yes. And in Darwin Evolves, I showed that while we are twiddling our thumbs, like this, waiting for mutations to come along, degradative mutations come along much more quickly that can oftentimes help alleviate a selective pressure.
So the thing I want to focus on here is because you made 3 points there. You made the overall point of maybe there are simple things that can evolve, the HIV binding site, for example. But if you get into more complex things, flagella, blood clotting, that kind of stuff, then that's beyond the limit of what we could reasonably say could evolve. So I want to stick with that, because then there's the point of Darwin Evolves, where you tend to have damaging or reductive mutations. Now, I would love to talk to you again about that. I would love, if you want, you could come back and we could talk about that for an hour. But that's a little bit orthogonal to what we're talking about today. But what I want to ask about is the limits here, really. Because so we've got a century of HIV. We know that this VPU protein evolved its new binding sites within decades of the crossover into humans. So we have what HIV can do, very complex new set of protein-protein interactions within a few decades. Okay. We've got other things, millennia, tens of thousands of years, billions of years. What's the limit on how complex a system could be? It's somewhere between the VPU interactions and a bacterial flagellum. Can we quantify that limit in terms of like this thing, given all the, all the time, literally all the time in the world, right? And all the cells and all the variation and every evolutionary mechanism, we've put things on either side of the line, right? But we haven't drawn the line. We haven't said where the line is. And that's really my big question, is how do we use these criteria to quantitatively draw that line?
Well, that was the topic of my second book, The Edge of Evolution. And the edge of evolution is the dividing line between what required design and what could be achieved by random processes plus natural selection. And I showed that in the development of resistance to the drug chloroquine, the malarial parasite Plasmodium falciparum took an enormous number of events to develop two crummy little point mutations in a pre-existing protein. And I went through a long argument to say that, well, okay, let's try to jump off that. And I said that if you needed to develop a set of two different binding sites, multiple binding sites in cellular proteins that did not have any selective values in the intermediates, then that is very likely a good place to draw the edge of evolution. And since then, I have seen no reason to change that conclusion and lots of reasons to think I was being too generous.
So with that malaria example, a couple points there. One is that I forget what number you used. It was 10 to a very large power. I forget what the number was. It was 10 to
the 40th.
20th.
Well, 10
40,
to the 20th for a chloroquine complexity cluster. If you
there you
remember
go. There you go. That's what I'm thinking. Right. It was a big. Right. It's a big number. Right. The probability is very, very low. Right. It's a big number. Now, the problem with that, using that as a quantitative standard, is that number actually comes from just a toss-off line in a review. It doesn't come quantitatively from the primary literature. The other problem with that, from just kind of an evolutionary perspective, is that those populations were evolving under extremely strong directional selection. Right? They're being hit with a very specific selective pressure, and you are weeding out tons of variation that's not only not going to help you with that, but has to be linked with the things that will help you with that. So you're in that example. And similar things are true for like evolving antibiotic resistance, where because you have to deal with whatever genotypes are linked with the beneficial resistance mutations that you find, you end up kind of clearing out, you do selective sweeps, you clear out a bunch of other variation in there. So that population size is not, and that rate of mutation, et cetera, et cetera, et cetera, is not representative of how long it would take, how many tries it takes to evolve that specific trait, because it's operating under very specific ecological conditions. On the other side of that, if you have populations in a situation where you have multiple different resources available and you could facilitate disruptive selection, right, and adaptive radiation, now you're going to see very rapid adaptation. And we see this, for example, when viruses switch hosts. You can see this not just in HIV, but you can see it in influenza. You can see it in this canine parvovirus 2 and 2A, where there was a temporary increase in their substitution rate when they jumped into their canine hosts. And so my point is that you're cherry picking very particular examples that are very ecologically specific, that are not representative of evolutionary processes and evolutionary innovation in the broader context.
Well, I disagree, surprisingly. I think
Why?
the selection, I think that the factors you mentioned for chloroquine don't matter, because in any particular poor person who is infected with malaria, the cells can undergo whatever mutations they want. Nobody's stopping them. So if such a person comes along and just by chance, a couple of mutations, the correct mutations had appeared in that person. And I remind the viewers that in one person with malaria, there's 1 trillion or so malarial parasites. If any one of them would have had the good mutation, then it could be selected. So I disagree that your criteria are appropriate. And if you look at other organisms in the wild and not viruses such as you mentioned, let's look at, say, in the past 10,000 years, look at the development of some resistance to malaria by humans. There's only a handful of different mutations that confer some degree of resistance to malaria on humans. And except for one, they're pretty much degradative. That is, they break genes or gene control elements. They're not adding up, as far as we can see, to any new system. As a matter of fact, they're breaking old systems. And the only exception is the sickle cell mutation. And that's hardly what you'd consider a propitious start for any new system to hold on to it. So there's no evidence that that's happening in these other organisms either.
So we've been going for almost an hour, so I do want to start to wrap this up. I don't want to take too much of your time, but I do want to just ask, with that specific example, this question applies to any of these examples, right? You say, oh, we've only found X number of examples that have evolved to do a certain thing. Does that represent the limit of what could evolve to do that thing? Does that represent the maximum, is my question, right? Because what I'm trying to do is quantify exactly where this dividing line is. So we say, okay, we've got X number of different phenotypes that confer malaria resistance. We have X number of phenotypes in malaria that confer resistance to various drugs. You could repeat this question across any number of the systems we're talking about, where you're saying, oh, we've only gotten X in this particular example. Does X in this context represent a maximum of what is possible via evolutionary processes? And if the answer is yes, how do you know that?
Well, because the answer is it's our best estimate. And it's our best estimate because, as I wrote in Edge of Evolution, these examples that I just mentioned, chloroquine resistance and malarial parasite and these various things in humans, occurred in the wild. We weren't trying to push them anyway. If the malarial parasite had been able to develop some brand new system to degrade chloroquine and get it out of there, and if it was more likely than what it did come up with, which are, as I said, 2 crummy point mutations in a pre-existing protein, then it would have, because it would have been more common, would have been more likely. So it would have stumbled across it sooner than the thing that it did. So that, I think, is our best empirical evidence for judging this. And I don't see anybody else trying to come up with an argument about whether there are limits or what those limits might be in the evolutionary biology community. Most people just assume, without thinking too much about it, that most things would not present a problem.
Okay, so I do want to point, I don't want to belabor this point, but I do want to point out that did not specifically answer the question. But I don't want to belabor. I don't want to belabor the point, though, because
I tried. I
have 2 questions for you. And one of them is kind of a wrap-up question. So my final real question, if you will, is in that same interview I referenced earlier from back just in January. You said towards the end of the interview that, at the end of the day, you don't need math to be able to show that something is designed. The criteria that allows us to show that something is the product of a mind is, the phrase you used was the purposeful arrangement of parts. So my question is, are there 0 systems that fall into the category of purposeful arrangement of parts that whose evolution we have directly documented? That seems like a subjective standard to me.
I'm sorry, I'm missing the question. You're saying
it was so. I'll actually read you the quote and then I'll ask. So you said you're arguing. This is talking about a future book that you'd like to write / are working on. I'm not sure. You're saying that arguing for the contention that a purposeful arrangement of parts is the only way that we recognize design, and of course we see that in abundance in biology. And so what I'd like to know is, of all of the systems that we've witnessed evolving, stuff that we've mentioned today, or stuff that we haven't mentioned, like there's other systems that meet the criteria for irreducible complexity. Another one I like is the placentas in lizards. Do none of these systems that we've observed meet the criteria of purposeful arrangement of parts?
Well, I would have to, the ones we talked about today, the HIV and citrate, I know they do not in my mind. But there are systems, I originally thought you were saying, do we need to use math to recognize purpose? And I don't think so.
Right, that was your contention, right?
But let me just say something else, that Darwin's claim to fame was that he came up with an idea that people thought would explain the appearance of design. So the strong appearance of design is something that everybody started with. It's not something that that people later added. For example, the eye. The eye looks designed because it's got all these interactive parts and so on. Certainly the eye fits my criterion of something that was designed. The examples that I talked about in my books, I've cited a number of examples, but no, I don't think the ones that we discussed today do.
Okay, so the important thing I want to point out here is that you said they don't meet the criteria in my mind, and that's the big thing I'm trying to get past, is that you can have a standard for what appears to be designed and should be attributed to design, but that standard is not going to be the same unless you can quantify that standard, right? And if I describe to you, oh, well, there's this protein and it evolved 3 new binding sites that involves between 4 and 7 new amino acids. I feel, if I describe that to you in a vacuum without saying it was HIV VPU, I feel like you would say, oh, that has the appearance of design. That it's not selectable and et cetera, right? So that's where I'm having a hold up here, is that this seems like a very subjective standard.
Well, I disagree. I mean, I just go back to everyday examples. If you look at Mount Rushmore, you can't quantitate that. What would be the likelihood of it? Huh?
That's my point. You can't quantitate that. So how are we doing this, right?
Would you think that it wasn't designed? Nobody would look at it for the first time.
I know who and how and when.
I'm sorry?
I know who and how and when for Mount Rushmore.
Well, suppose he was lying. Suppose a big story came up and turns out he was lying and wasn't him. How would you know? I mean, you think it was designed, not because some guy stands over here and says, ha, I designed this thing, and you look over and you don't see much of it much. You think it was designed because of the structure of the object itself, the strong resemblance to historical figures, and so on. You'll have to wait for my new book.
I will anxiously await it, because I feel like this does need to be quantified, and this actually is a good lead into my last question. So where I want to leave this, before I say this, I want to thank you so much for giving me so much of your time. This has been really good, and judging by the comments in the chat on YouTube, people are really enjoying this.
Okay.
So my last question is this. So we've been talking for about an hour about, pretty like nuts and bolts stuff about this hypothesis, irreducible complexity, and its implications for evolutionary theory. Now, you're a legit scientist. You've gone through this. You've published work on how biochemical systems work. Like, this is you know how this process works. And you know what it takes specifically to say, here's a thing, and I'm going to convince you of a thing, right? Here's how this system works. I'm going to convince you that this is how it works. You're also familiar, I'm sure, with the many recent-ish, decades examples of the overturning of an entrenched paradigm. Just within the second half of the 20th century, you've got things like plate tectonics, ribozymes, reverse transcription, prions, even Helicobacter causing gastric ulcers, right? These were all ideas that were outlandish when they were first proposed, and took, in many cases, a decade or more to kind of bring people to their side, right? It really took a lot of work to get people on board with these ideas. So my question is that, why are you not doing that for the idea of irreducible complexity? Why, instead of like, I'm gonna sit down and we're gonna show, here's a system that can evolve under certain conditions, population conditions, ecological conditions, amount of time. But these systems, this set of systems with these criteria, can never appear. And we can draw empirical conclusions from that and be able to quantitatively draw this line and say that certain systems cannot appear through evolutionary processes. Why are you not doing that work to convince people instead of writing popular level books?
Well, because it's a simple idea and it can be explained simply, even to scientists. The question that you write or you pose is equivalent to saying, well, suppose I went into a lab and knocked out, say, all the genes for the components of the bacterial flagellum and grew it for a long time and said, look, no flagellum has occurred. So who's going to be convinced at that? The nice thing about Darwinian evolution is you asked whether intelligent design was falsifiable. I think Darwinian evolution is pretty close to unfalsifiable, because if you can't evolve something complex like, say, a flagellum, then the folks who oppose that say, well, you didn't wait enough time. You didn't start with the right bacterium. You didn't have the right selective pressure, yada, yada, yada. So the problem is that the claim of Darwinism is that some undirected path could produce this.
Okay, we're good.
But it doesn't say which one. It says some. And that's essentially impossible to rule out every imaginative pathway.
To be honest, I feel like that was a little bit of, I know you are, but what am I? But I mean, that's what.
All right, I missed the joke, but
that's what it. No, that's what it comes out. It's saying, yeah, that's what that came off as to me, honestly. Okay, so I will leave it at that, everybody. This has been Dr. Michael Behe talking about irreducible complexity in 2021, which is the 25th anniversary of the publication of Darwin's Black Box. Dr. Behe, thank you so much for coming on today. I really appreciate it.
Thanks for having me.
I'm going to awkwardly have to remember there's 2 buttons to press to end the stream. Okay, bye, everybody.